In this video, we present a self-supervised approach for learning to ignore distractors for robust monocular visual odometry in urban environments. Standard approaches to visual odometry that use outlier rejection methods such as ransack fail when the scene is predominantly occluded by an independently moving object, like the bus. Our approach on the right ignores distracting objects in the scene and is robust to such situations. To achieve this robust visual odometry, we predict a pixel-wise ephemerality mask as shown. Ephemeral objects which don't belong to the underlying scene and are poor candidates to use in VO are shown in red, such as vehicles and pedestrians. Objects which are static and are good candidates to use in VO are shown in blue. Our learned ephemerality mask highlights the bus, allowing us to calculate our trajectory from only the static parts of the scene. To train our system, we use a data collection vehicle with a stereo camera and a LiDAR scanner and collect numerous overlapping traversals of the same route. These sensors enable us to generate an optimized 3D point cloud of our route without any ephemeral objects such as cars. We utilize all this data to automatically label images with ephemerality masks to train a deep convolutional network. Our approach needs no manual annotation and is fully self-supervised. To build ephemerality masks for training, we first compute the true disparity in normals using an offline dense stereo approach. We project the prior 3D static structure into the image to create the expected disparity in normal images. In the presence of traffic or dynamic objects, these will differ considerably. We compute the ephemerality as a weighted sum of these differences. Using this self-supervised approach, we can automatically generate vast quantities of labels under different lighting, weather, and traffic conditions. We use these labels to train a deep convolutional network to predict both the resulting pixel-wise ephemerality masks and disparity. At runtime, we use a vehicle only equipped with a monocular camera and produce live disparity and ephemerality masks. These outputs are fed to a sparse or dense visual odometry system. The disparity prediction gives our pose estimates the correct metric scale, and the ephemerality masks enable robustness to distractor objects. Our ephemerality-aware visual odometry systems outperform baseline approaches with reduced average odometry drift and significantly improved egomotion estimation in the presence of large distractors such as moving vehicles in urban traffic. We evaluated our approach on more than 400 kilometers of driving from the Oxford RobotCar Dataset, covering a wide variety of traffic, lighting, and weather conditions.